morning, guys. We are back here to the second class of this course. Yesterday we saw um, fluctuation relations. I mean, in classical and quantum mechanics. Today are going to start. I think that's the most difficult part of this course. It's general relativity. I mean, GR for me is the worst theory in physics. I mean, in the sense of understanding it, is extremely difficult because it's absolutely nonsensical, and it's much more non-intuitive than quantum mechanics. Quantum mechanics is easy. I mean, it's just a theory that tells you how probabilities unfold on space-time. That's okay. The problem here is that we are dealing with the dynamics of this space-time itself, and this makes things extremely worse and far from intuitive. So, of course, I'm not going to take a whole course in general relativity. This would take too much time, but hopefully, by the end of these lectures, you will understand the basic mechanisms behind general relativity and why it is the way it is. So please ask questions. I mean, don't let things go forward, otherwise it's going to be complicated. We start with Newtonian things. So this is a picture by this is Aristotle, this is Galileo, and this is Descartes. Of course, this meeting never happened. We have centuries splitting these guys here, but why they are here? Because these guys started to think about the nature of space and time itself, and for them, space is just a thing that happens between things. So between me and that chair, there is a space, and time is a thing that happens because things are changing. So what does this mean? It means that space and time have no physical existence. They depend on things. They exist because things exist. Newton changed this. Newton was the first guy that thought, no, we need a mathematical structure for this guy, and this guy exists independent of other things. So Newton, one of the things that Newton did beyond calculus, beyond universal gravity, beyond many other things that he did. And I hope that will become clear why he did this. So this was old thought about space and time. Then came this guy, Isaac Newton. Okay, Isaac Newton was a brilliant guy that invented calculus in order to define acceleration, because he needed to define acceleration with respect to something. This something is the structure of space-time that he defined. Let us see if this becomes clear. So, Newton's law. Everybody knows that there are inertial reference frames, okay, where Newton's law of inertia hold. And in any of one of these frames, these equation hold. Well, everybody knows this. This is the linear momentum. This is the force. So this is Newton's second law, and this is the Newton's third law. This is the force on particle I due to particle J. So this equation holds. It doesn't hold for electrodynamics actually. You see, it just holds on mechanical systems. So from where these laws came from? These simple observations. Space-time is three-dimensional and Euclidean. What does this mean? This means that, I mean, the surface of the Earth seems like to be flat. I know some people think that the entire Earth is flat, but a small part of the Earth is flat, which means that if you draw a triangle here, the sum of the internal angles will add up to pi. I mean, no matter which triangle you draw, this will be the result. So this is the meaning of Euclidean here. So we knew this. Galileo's principle of relativity. If something holds in one inertial reference frame, so it must hold in any other one. This is a consequence of these two symmetries here: homogeneity of space-time and isotropy of space. Well, homogeneity of space, because if I perform an experiment here and I perform an experiment there, it should be the same. The results should be exactly the same. And if I perform an experiment today and the same experiment tomorrow, the result is going to be the same. So this is the meaning of homogeneity of space and time. Things don't change. And isotropy of space. I mean, if I rotate the entire experimental system, the result should be the same. So this is isotropy. Isotropy of time, it makes no sense because time is one direction, so there is no, but space is isotropic, as far as you know. Okay, and this guy is very important because we know that if you know the position, the velocities, at a given time, we can determine the entire motion. This means that we don't need to specify acceleration, and this is a consequence of homogeneity of space-time. I mean, things don't change if we don't do anything on the system. This implies that Newton's law must be of second order in time. It cannot be in first order because you break down time reverse, and you cannot be any odd order because of time reverse symmetry that we have, and it cannot be bigger than second order in time because we don't need to specify acceleration. So that's why Newton's equations of second order in time. Oh, determinacy. Well, suppose that you have this microphone on the table. If we look at here, I mean, we can keep looking at the microphone and nothing will happen unless we do something on this guy. So, but this time is going on, so it's flowing in time. If time is not homogeneous, then this thing changes, and we're going to need to specify acceleration. Oh, so that's the point. So we simply see that nothing happens here. So I just need to tell the position and the velocity, which is in this case is 0. I can tell you that in the next morning it will be here at the same point in space, but in another point in time. So I don't need to specify acceleration. Is that clear? So that's why Newton a second law is of second order in time. It's not because it's funny, but because that is, I mean, we need to reproduce experiments. So all of these things implies that Newtonian space-time is not a vector space. Newtonian space-time is an affine space. And this is a very important. Affine space is just a set, what you call A, along with this the vector space, which makes translations in space. And this is important because an affine space is not a vector space in the sense that, well, it is a vector space if you remove the origin. So we have no, due to Galileo's principle, we have no special point in space, what we call origin. And if you remember the postulates of the vector space, the axioms of the vector space, one of them is that there is a special vector, which is the null vector. So in affine space, we don't have this. We define translations. That's the role of the vector space here. And the sum of two of points is a vector. The difference of 2 points in this guy is a vector. But the sum of these 2 points is not defined. And we call every point in this space, in this space-time, an event. Every one of these guys is an event. So there isn't a way to draw a picture representing space in Newtonian space-time. Space is an equivalent classes of simultaneous hypersurfaces. All of these blue things happen at the same time. That's very important, extremely important actually. So this is the mathematical structure introduced by Newton, and I mean there is no other way to do this, to do physics. We needed to do this, and Newton simply thought, no, space and time, they do exist, they are physical entities, and they are described by this thing. But Newton still thought about the time and space idealized by Aristotle and Galileo and these guys. He thought that there were two different things, two different concepts, but he didn't understand at the time. Actually, he didn't like this thing because his theory predicts action at the distance. He didn't like this thing. He wrote this in the Principia, but the problem is that he was unable to solve this problem. I mean, we needed to expect 200 years and Albert Einstein to solve this problem. So it wasn't an easy problem to solve. But that's the mathematical structure that those facts that I just showed to you imply. There is no other way to do physics. And Newton did this because he wanted to describe the motion of things, independent of other things. And how do you do this? Calculus. That's why he invented calculus. Because he knew that to describe motion, I need to describe how things move in space and how fast things move in space. So I need derivatives. And I need derivatives with respect to some structure, some mathematical structure. And that's behind Newton's theory. That's the mathematical structure that we see there. Nobody tells you about these things in basic courses of physics because, I mean, this is too much information. You don't need this. You need to understand this to understand general relativity, but not to understand basic physics. So, here is okay. Then comes time. Time is just this linear map. Everything is defined as a map. So it goes, it takes an event here and takes to the real line. The real line is the time. So the kernel of this guy, which means that the action of this guy on events that goes to, on distinct events, on the difference between two events, A and B, let's call it. If A and B belongs to the blue surface here, the action of this guy gives 0. So that's the kernel of the guy. So the kernel of these guy are the points here, are the vectors in these blue hypersurface. It's a 3-dimensional hypersurface. These are the simultaneous hypersurfaces. On these guys, we define distances. So to define distance, we need first to define time, what time is. Because distance are defined not between one of the hypersurface and the other. They're defined in each one of the hypersurfaces, because distance is defined between simultaneous events and not different time events, because it makes no sense. So spatial distances are deeply linked to simultaneity. And we know that when you go to special relativity, simultaneity changes, so spatial distance and time distance must change. That there is no other way, because I mean, distances are defined like this. Okay, that's the way we measure things in Newtonian theory. Okay, then we simply define the metric. As I told you, the difference between 2 points in this space is a vector. So as a vector, we can define a norm, and from this norm, we can define the inner product and the metric on this guy. So this is the usual Euclidean norm of a vector. That's the way we define distances in usual classical mechanics. And A and B belongs to the same simultaneous hypersurface. Oh, by the way, did you see the lecture notes in the in the website. Well, they are there. Okay. Hopefully they are there. So what we call Galilean space-time is the set of the affine space, the set of events that happen in time, the time functional, and the distance. So this entire thing is what we call Galilean space-time, where Newton's theory is built. Okay. Why I'm doing this? Because Einstein changed these things, and we're gonna see how he changed everything here. Okay, and of course, the set of affine transformations that preserve this structure is called the Galilean group, which is just translation in space, translation in time, and rotation in space. That you can build any element of this group by combining these three things. Okay, and uniform motion, but this is, you can see the translations. I don't know if he's gonna talk about Galilean group in his no, but I mean it's a symmetry group. So everything is okay. Let us start to complicate the things. Now we need to do calculus. How we do this? By introducing what we call reference frames. That's why reference frames I use it for. I mean, because we don't know how to do calculus in this guy here, but we know how to do it in this guy. In the Euclidean space we know. But here is complicated because we don't understand that thing. So we introduce these reference frames in order to perform calculus, because we know that every physical law is expressed in terms of differential equations. So we needed to define derivatives, and that's why we introduce this thing. And a reference frame is nothing but a way to label events. In the case of space-time, Newtonian space-time is easy because the entire space-time is isomorphic to this guy. So we simply pick up these guys and take to the and define a map that takes events in this guy and takes to this guy, and then we have a coordinates, and then we can do calculus there. But we needed just one reference frame to cover the entire space-time. That's why we simply don't talk about this in basic physics. But when I go to general relativity, this is not true anymore, and we need a bunch of these guys and coordinates that have no meaning. Coordinates have no physical meaning at all. This factor becomes extremely dangerous there, because if we misunderstand these things, then we can make huge mistakes in calculations. Because physical distances are very different from coordinate distance. I can have coordinate distances that is infinite, and the physical distance is finite. Because I mean, just labels. That's the first thing that we should keep here. Coordinates are just labels for the events. But of course, there are rules. I need to define these in order that no different two events have the same coordinates, the same labels. Otherwise, it must be unambiguous. And since we are defining differential equations, we assume that this map that takes things from here to here, is of class C infinite, which means it's smooth. So we need to do this. But otherwise, it's arbitrary. We can take whatever coordinate we want. It's just a set of labels. So mathematically speaking, is this. Well, it's infinitely, all of the derivatives exist. So I can define, well, we don't actually need these infinitely many derivatives, but we need a number that's enough. I mean, you need Yeah, the order of the derivative. It must exist. So mathematically is this. We define a map phi that takes events this guy and takes to this guy. This is the space. This is the real line representing time. And this is the map here that takes this point to here. So here, I mean, the output of this map, we call the coordinates of this point. So, but we can define it any other map here, and the coordinates of this guy in these given by this map are here. So we can think about Cartesian coordinates and spherical coordinates. I mean, it's just different labels that I put to the same point, to the same event of the space-time. Okay, and then of course I can define this map with taking a coordinate here, taking back to the manifold. That's why it must be invertible. And then take here to here. So this is just a coordinate transformation. The arrow here is inverted. The arrow here should be here because I just transforming this coordinate to this coordinate, so the arrow is inverted. And we impose that this map can be differentiated. I mean, infinitely many times. So it's a smooth map. So this is what we call a coordinate system. And this is what we call a coordinate transformation. So there are rules of this guy, and there are rules of this guy, but in the end it's just easy like this. Why I'm doing this? Because in general relativity, that's the only way to do things. We can pick up in Newtonian space, we can pick up a single coordinate system to cover the entire space-time. In general relativity, this is not possible anymore. We have a bunch of them, and these cause the problems because we cannot compare vectors in different points of space. And if you cannot compare vectors, you cannot compare energy, you cannot compare anything. So it's extreme. For instance, there is no global conservation law in general relativity. Conservation of energy. We cannot say that energy is conserved. This makes no sense. And then you see the problem for thermodynamics. So coordinates and distances. This is one of the most important things. And Einstein himself told that general relativity was read many years ago. He published it in 1915. But it took him several years to understand that this is like. I mean, that coordinates has no physical meaning. They're just labels. Physical distances in space or time are defined by the metric as a function of the metric that we're going to see this not today. It's going to be impossible. Actually, it's going to be impossible to finish this 46 slides today. It's too heavy. But let us see how far it can go. So that's the most important thing that we pick up from these things. We define a coordinate system by this map, and we're just labeling events. It has no relation to physical distances. In Euclidean space-time, Galilean space-time, the physical distance will be the same as the coordinate system, the coordinate distance. But this is a consequence because of Euclidean geometry. It's not true in general. So, dynamics. Dynamics is another map. You see that I'm defining everything in terms of maps because there is no other way to do this in general relativity. So it's better to understand how to do this in Newtonian physics that we understand, and then go smooth into GR, where these things is quite abstract. But we need to define this thing that's a curve. This is a portion of the real line, an open interval of a real line, and we need to define open intervals here because we need to define because problems in continuity of derivatives. So if you remember calculus first course, we define derivatives in terms of open sets. Otherwise, you have problems in continuity and things like this. So we are always talking about open sets here. So a curve is just a map from open set of the real line to this guy. And from this we can define the word line, which is this guy. The word line of something, of some point. It starts here and goes here. So the velocity and acceleration are simply defined as the derivative of this guy in this direction, in the direction of time. Okay? And this guy here is called the configuration space. This is what we call configuration space in classical physics, classical mechanics. Newton's law. Newton's law, if this guy determines the motion, it must determine the acceleration. So the second derivative must be given by some function of the coordinates and things like this. And this function is just this map. This function is the force, of course, and this defines the mechanical system we are dealing with. Okay, so Galilean invariance in time says that in a closed system, this guy cannot depend on time. More than this, it implies that they cannot depend on the coordinates itself, but only relative coordinates, because they don't have an origin, they don't have a special point in space. So it must depend on the relative distances. It's actually isotropy of space implies that it cannot depend on the vector nature of this guy, but on the absolute value of this guy. Okay. And this is, this, of course, Newton's second law. That's the way Newton postulated his law. Based on experimental facts that we have access since Galileo. So, the role of geometry here. The role of geometry is defining acceleration. We'll come back to this thing later, but the important thing here is that Newton needed to put this mathematical structure, to postulate this mathematical structure to define acceleration, because we think that acceleration is absolute. We say this in Newtonian physics, but we need to define it with respect to what we are accelerating. That's Mach's principle, and all of that discussion cares about is you are accelerating with respect to what? And the answer is simple. You are accelerating with respect to the static geometry of the space-time. You are accelerating with respect to Euclidean geometry of space. That's why Newton needed this thing. That's why he built this thing. And that's why everything changes here. And we're going to see that's the key point to understand why general relativity is a theory of gravity and at the same time a theory of space-time. The key point is acceleration. When you understand what's the meaning of acceleration, what's the meaning of being inertia. So the meaning of space-time here, the meaning of space, the mathematical structure of space-time introduced by Newton, it should tell you what's accelerating and what's not accelerating. So the physical meaning of the space is to define inertial reference systems. There are those that are not accelerating with respect to the Euclidean structure of the space-time. Einstein changed all of these, and that's why gravity is equal to space-time, and it must be curved. Because the role of gravity is just to break the Euclidean character of the physical space-time. We're going to see this in a bit, but this is the important thing here, is to understand that acceleration is not defined with respect to nothing. It must be defined with respect to the space-time, to the Euclidean space-time. Okay? That's the main point of all of this discussion. Acceleration is the key point in Einstein theory. So that's the causal structure of the space-time. if I have an event here, I should put a point P here, but think that's a point P here. This P here. It's here. So this blue thing here is the present of P. All of events that happen at the same time at P. So this guy here, anything above this hypersurface here, is the future of P. So P can influence any event, any one of these. Because I mean there is no limit in the speed of propagation of information or interaction. So P can influence any one of these events, and this is infinite. So that's why we need actual at a distance. That's the meaning of actual at a distance. I can influence anything, and anything below this hypersurface is the past of P. So that's the causal structure. This can influence P, and P can influence anything here. So we have the present, we have the future, we have the past. That's the usual structure Newtonian space-time. So that we know. Let us see special relativity. Special relativity is the same mathematical structure behind. It doesn't change. It just changed some notions, but the mathematical structure behind it is the same. Newtonian space-time. We have an absolute meaning of simultaneity. Everybody, because time is absolute, so we have everybody sees the same hypersurface. So the present of an event is the same for everybody, as well as the past and the future. So special relativity, they change these things. I mean, those hypersurfaces will depend on the motion of the observer. So these things change. This is because of this. That is a finite speed of propagation of interactions. So physical quantities must be independent of coordinates. This is true in all physics. So what we have in Newtonian space intervals and time intervals are invariant. If I change the coordinates by a Galileo transformation, the space intervals and the time intervals don't change. No? We know this in classical mechanics. In special relativity, only the space-time interval is invariant. Space intervals or time intervals are not invariant. We know this because you know something like twin paradox, or which is not a paradox actually, but the so-called twin paradox and space contraction, length contraction, and time dilation. So we know that these guys are not invariant, but the space-time interval is in special relativity. So special relativity is based on two postulates. This is the first one, the principle of relativity, that says that all inertial reference systems, the laws of physics must be the same, which is different from Newton. Newton said the mechanical laws are the same. But as you saw, the third law of Newton doesn't hold for electrodynamics. But here, Einstein said that no, all the laws of physics must be the same in all of these guys. And the universality of the speed of light. It could be other number here instead of c. Yeah, it can be any one. But we needed to bound the velocity of interactions, because this is what we actually see here. So this is quite natural, because we want to do physics that are independent of our definitions of those maps that I just showed, that are coordinate system. I mean, those things are arbitrary, so we cannot rely physics on these things. And then this is an important thing. A particle at a certain point of space at a given instant of time, it can influence any other point in space in subsequent instant. This is actually at a distance. I mean, there is no bound. In special relativity, no. It cannot, because I mean there is a finite speed at which interactions can propagate. So the entire notion of present, past, and future must change. That's why Einstein introduced his space-time. Actually, Einstein did this, but who actually formalized the space-time in this way was Minkowski, the mathematical guy that mathematician that actually formalized this structure, mathematically formalized. So what happens that at each event here P, we define the light cone at each one. So these blue lines are 45 degrees, because you see C is supposed to be C here, because this guy should be the same dimension of this guy, so C is 1. So I always use this guy as 1. So this guy has a 45 degrees inclination. That's where light walks. And then this defines the future of P. These guys are the events that can be influenced by P through a finite speed. You cannot have a line crossing this guy, because a line crossing this line, this blue line, should travel, the signal should travel faster than light. But you cannot do this, so we can only have curves that are less inclined than this guy. So we are trapped here in the future light cone. The past light cone are the set of events that can influence P. And there is no such an notion as the present of P. But there is no way to say that that event and that other event happen at the same time. This makes simply no sense if we don't specify with respect to what we are measuring time, which is very different from the Newtonian physics. Okay, so that's the causal structure of space-time in special relativity. And at each event of space-time, we define this light cone. So we have a bunch of light cones, one of each event, and that's it. And here we have no causal relation between this point here and the points here, which is a 4-dimensional set, actually. And this light cone is a 3-dimensional hypersurface. It's a hyperbola. That guy is the only thing that, well, as there is a mu and a nu here. I'm using Einstein convention, which means that repeated index just sum. And here we have 4 dimensions, so the first one here is 0, 1, 2, and 3, which means time and the 3 space coordinates. And this is the interval that I'm considering here, that the space-time interval. This is invariant. This is the only thing that is invariant under the symmetry group of special relativity, which is the Poincare group. Okay, so the strange thing is here we have three different sorts of intervals. We have when this guy is positive. When this guy is positive, we are outside the light cone. So this guy is space-like interval, which means that we cannot, nothing can go from one event to the other. Absolutely nothing, because light cannot. These guys are a special thing. It's where light lives. Light can only walk in these sort of intervals, which we call new hypersurfaces, with here represented by these surfaces here, which means that, I mean, this is a consequence of the fact that everything walks at the speed of light in space-time. But we can walk through space with a velocity smaller than light, and then we cannot walk on time with the velocity with the speed of light. But light can. So for light, there is no notion of time. I mean, we simply cannot measure that. There is no proper time for light because of this. And that's why we see time dilation, for instance. If I'm moving, if I'm just standing, I'm walking just in the time direction with my full speed, with the speed of light. But if I move in space, I must decrease the time, the velocity in time. That's time dilation. That's just, geometry. We are just measuring different events. There's nothing strange in these things. And here is where we walk. This guy as a negative distance. So you say, no, this cannot be a metric. Yeah, it cannot be a metric. A metric, properly speaking, a metric should be positive, but here is negative. But it's okay. That's why we call the space-time here pseudo-Riemannian space-time, because the metric is not positive defined. We have this guy, and this we call a Lorentzian metric. It has this signature here, plus, minus, minus, minus. If I change the minus here and plus, 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 it's going to be the same. It's just a matter of convention. And that's why we usually define proper time by this relation here, the minus sign, because we want proper time to be positive. So everything is redefined here. I mean, space, the past, the future is redefined, and there is no present of p. There is no notion of present. So that's the mathematical structure behind space-time. And this is an important thing. This is the physical length of something. We just define like this. You see the metric here? That's the metric, the Euclidean metric. The Minkowski metric, actually, which implies that space has Euclidean metric, Euclidean structure. So that's the usual thing we see. But if I change this metric here by a general one, then this guy is going to be different from the physical distance between the coordinates, because here we have the coupling. All the coordinates are being coupled to each other. So that's the definition of physical distance, and that's the definition of physical time intervals. And when the metric changes in time, in space, this guy changes. It's simply like this. I mean, it's a consequence of the geometry of the space. And the minus sign here is because of the Lorentzian signature of the metric. And lambda here is just a parameter of the curve. It can be whatever. So, as I told you, the symmetry group is the Poincare group, which is just translations in space and time, and Lorentz transformations, which are rotations in four-dimensional space-time. That's, I mean, that means that this keeps the equations the same, and this keeps the space-time interval the same. So that's the symmetry group of special relativity. So just yeah, this is just, I mean, this guy here. Oh shit, no. So the definition of a length is this. If I have some curve, it doesn't matter if it's space-like or null-like or whatever. This curve is parameterized by some parameter lambda. I don't care. It can be time. It can be whatever. Or for light, it cannot be time. But and then I want to compute the distance between this guy and this guy. Let us call lambda 1, lambda 2. And here, the metric defines this guy, the vector here. So the length of this guy is just the integral of this guy. So if I write this in coordinates, I have this thing. So that's the geometric definition of distance. And time is the same thing, but this is the integral here is performed over a time-like curve, and the integral here is performed over a space-like curve. just the geometrical definition of distance. And then that's why you see that we say that clocks that are moving with respect to each other ticks differently. Okay, although for each one of them they tick exactly the same. It seems that this is a consequence of the motion of things. So this leads people to think that clocks that live in different points of space-time or of space will tick differently because of the action of gravity. But this is not true. I mean, the fact that they tick differently is what we call gravity. It's not an effect of gravity. So these are very different things. There is nothing happening with the clocks. And here, there's nothing happening with the clocks. Clocks and rules are doing what they do without being affected by anything. It's just, I mean, the geometry of space-time makes this different. When you compare things, you see that you're actually measuring different events. So things must be different. That's the point. We are only talking about geometry. Special relativity and general relativity are not theories about things that live in space-time. The theory is about the space-time itself. So, is that okay, guys? Because now things get worse. And, well, it's going fast, actually. I mean, time is flowing fast. They're recording. You need to use these. Oh, turn it off.
Okay. Just a little thing. Can you the previous one? Yeah, I think that by the way you choose the signature, it should be like space like should be negative, and time like should be positive, right? Or am I getting something wrong? Yeah, because if you take a curve with velocity in the t direction, yeah, it would be positive.
Oh, that's true. That's true. That's true. Yeah, I mean, inverted these guys. Yeah. Okay, just that's why I use. That's what happens when I mix different books.
Personally, I like the signature minus plus, but
yeah,
it's like a religion. You can choose it.
Yeah. Well, but the thing that the physical implication doesn't change. I mean, they're the same. So if you find some typo in the notes, please let me know that I'm correct and upload the correct one. There will be a bunch of typos actually. So the GR. I will try to convince you that GR is a field theory for gravity, but that it also describes space-time. And this implies that space-time must be curved. And then tomorrow we get into the mathematical description of this thing. Otherwise, it's going to be too much. So, as you saw, Newtonian and special relativistic space-time, they have the same basic structure. I mean, space is Euclidean in both of these things. And if you take the low limit velocity of Newtonian theory, that light cone just, collapse to the hypersurfaces, simultaneous hypersurfaces of Newton theory. And in this sense, Newtonian theory is the low velocity approximation of special relativity. But the important thing is that space and time are physical things that do exist, but they don't have dynamics. What Einstein did is to put dynamics on these things. I mean, these things should be dynamical. No, no. No, 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 no. No, but you can define that. That's a good question, actually. But if at every event, you can define the future direction of time, of course, and perpendicular to this, you can define a hypersurface that is simultaneous to P. That's not the present of P because this simultaneity hypersurface depends on the observer. But you can define this three-dimensional hypersurface, which is perpendicular to the time direction. Actually, we do this every time when we're solving physical problems. We establish a coordinate system, then establish the future direction of time, and then here we define our problem. We define the space, we define the quantities at a given instant of time, and then the equations just take this thing forward in time. So what Einstein did was to change this thing. I mean, he put dynamics onto this issue. So general relativity, it keeps the same thing. These guys are still physical, but they have dynamics. They have some dynamics, and for this, it replaces this metric, which is the metric Minkowski metric. It's flat, which we call flat spacetime metric, by a general one that obeys Einstein's equation. So Einstein's field equations are equations for this guy, and not for particles that live on this guy. Let us see how he built the theory. So, first of all, why do we need a field theory for gravity? That's the first question. Electrodynamics, the answer is here. If we pick up these Coulomb force, with the force between two charges that are separated by distance r in the direction of this guy here, we see that if we move one of the charges, the other one will feel it at the same time. So this guy is contains x of a distance. So that's a problem because this is not compatible with special relativity. But we know that Maxwell's equations are actually compatible. So what's the problem here? The problem is that Coulomb's force is not the force between two charges. It's just the limit or the static limit of this force when things are not moving or moving extremely slowly. So to describe the electromagnetic interaction and the interaction with the charged particles, we need Maxwell's equation. So we need a field theory. So we need the potentials, which are the fields. We need Lorentz force, which governs how things move interacting with this field. So that's Lorentz force. And we need Maxwell's equations. Oh, this I don't know if you are used to this form, but this is the covariant, let's call it covariant form of Maxwell's equations, because when you say that the laws of physics are invariant under coordinate transformations, only if they are written in terms of tensors. We're going to see tensor law transformation tomorrow, but this is Maxwell's tensor, so this is a tensor equation, and this is invariant. If I change coordinates, the components of the tensor change, but not the tensor. So the equations keep the same. That's why this is strange notation, but these are the set of Maxwell's equations. And this is just Lorentz force that tells you how things move when interacting with these electromagnetic field. Okay. So this is a field theory. A field theory tells you that there are actually no forces. The interaction between one thing and the other is mediated by the field, and the field is causal. So there is no action at a distance. The propagation of the interaction is finite. In this case, it's the speed of light, because we're talking about Maxwell's field. That's why we need a field theory for gravity, because Newtonian expression for the gravity is the same thing. So how we solve this thing? Well, at that time, Einstein knew Maxwell's theory. He said, look, this is a field theory. I need something like this. Otherwise, to avoid this strange thing, because this thing tells that if I remove the sun, the Earth will feel at exactly the same time. But this is not true. We know this. It will take at least 8 minutes. And then Einstein thought, no, I need a field theory to describe gravity. So gravity must be described in terms of a field theory. And this field should account for the degrees of freedom of gravity. Okay? There is no space-time here. It's just electrodynamics. Electrodynamics is a field theory that lives on top of a space-time. It doesn't matter if it's curved or not, but it's a field that lives on top of another field. Here, Einstein thought that was the same thing. I mean, gravity would be a field living on space-time. He realized that these two things must be the same after this. But, I mean, I think that's clear why we need a field theory to describe gravity, because we need locality. So, that's the field theory. The same thing. We have the field. We have the geodesic equation, which tells you the motion of particles that are interacting only with gravity. They walk on geodesics, what you call geodesics. So that's equivalent to the Lorentz force. And we have the equations governing the field. We are going to understand all of these things here, but this part is the curvature of space-time, the curvature, and this guy is the matter, energy matter. We're going to talk about how we derive this equation, not derive, but postulated this equation in a physical, sensible way. But now this slide is just to show you that you have the same components of the field theory. We just need to define who this guy is, who this guy is, and who this guy is. Okay, but it's the same thing. We have a field equation, a field theory for gravity. But then comes the problem. Where is space-time? And the problem is acceleration. That's the point. That's Newton's bucket experiment. So if you have a bucket that is with the water here, the surface of the water, this is ChatGPT. Again, it's amazing. Yeah, it's amazing. All of the images, like most of them. So if I start rotating the bucket, what happens with the water? Nothing, because the water is still there. I just rotating the bucket. But then there is friction between the water and the wall of the bucket. That just start rotating the water. So here I have the bucket and the water rotating. And when the water is rotating, we have a curved surface on the water. That's okay. And then we stop this arrow. This arrow should not be here. Sorry. The bucket here is, it's just I stop at rotating the bucket, but the water is still rotating because of inertia. It's rotating. But then the friction between the water and the surface, we stop the water, and the surface at the even go back to the initial state without rotating. What happens here? The bucket is rotating, the water is standing. The bucket and the water are rotating. And here, the water is rotating, but the bucket is not. So we cannot define acceleration of the water or acceleration of the bucket with respect to the water or with one another. This must be defined with respect to something else. This something else is the geometric structure of the space-time. Actually, this is accelerating with respect to the Euclidean structure of the space. That's the way you explain this experiment. There is no other way. That's why acceleration, that's why space defines what is accelerating and what's not accelerating. You are changing with respect to the Euclidean structure of the space. That's extremely important point that Einstein realized through the equivalence principle. He just realized that when a guy is falling under the action of gravity, forgetting friction and other things, when I'm falling down, that's why I bring this. Look, if I hold this thing here and I just release it, I'm not inertial, because I mean, when I release it, the ball from my hand, it's supposed to be here, because nothing is acting on this thing, but it falls down. But think that I'm just falling with the ball, forgetting friction. So just falling with the ball. What happens if I just open my fingers? Nothing. The ball is to be here. Nothing will happen. And if I just kick the ball, it just go on a straight line. You can think about you are closer in a box and you are falling down. There is no gravity there. You feel nothing. The laws of physics are the same as you would be in an inertial reference system. So Einstein realized that the role of gravity is to redefine what's inertial or not inertial. But who defined it, who is inertial or not in Newtonian or special relativity space-time? The structure of the space. So space defines what's inertial and what's not inertial. If gravity does the same, then these things must be the same, because the same cause must be associated with the same effect must be associated with the same cause. That's why Einstein said that this was the happiest thought in his life, because he realized that gravity and space-time are actually the same thing, because of acceleration. That's the key point that acceleration played in Einstein theory. So in this way, gravity just redefining what you call acceleration. Because I mean, we know that if you are in orbit around the Earth, you feel no gravity, you feel nothing actually. I mean, the laws there, all the laws of physics will be the same. Will follow the special relativity theory. That's the equivalence principle. The equivalence principle says that locally, physics follow special relativity. That's the point. That's the equivalence principle. But this makes inertial reference frames just, I mean, a mathematical abstraction. Actually, there isn't no inertial reference frame in nature, because there are no homogeneous gravitational field. Because, okay, if I have two of these balls and release both of them, what happens if I'm following is this. I will see this thing. And this is not inertia. And this is because of tidal forces. So that's why the equivalence principle is just local. That's the meaning of local here. It's in a small region of space and space-time in which I cannot see the breakdown of Euclidean geometry. That's another way to state the equivalence principle. So if I cannot tell apart, if I cannot detect the breakdown of Euclidean geometry, then I am in an inertial reference frame. That's the content of equivalence principle. And that's why gravity and space-time are exactly the same thing. Because the role of these two guys is just define inertial observers. And this implies what? This implies that gravity, a Newtonian special relativistic space-time are just particular cases of this field when there is no gravity, when I cannot detect gravity. If I can detect gravity, I must break down the Euclidean character of space. Otherwise, I cannot detect gravity. And this implies that space must be curved. There is no other way. It cannot be Euclidean. So that Einstein realized it in when he had the idea of the equivalence principle. He understood that gravity and space-time is the same, and for this to be true, the space must not be Euclidean. So space-time must be curved in general. And this is gravity. It's just a manifestation of the curvature of the space-time. So gravity is not an interaction between things. It's just because we are living in a space-time that's curved. And we see this curvature. And we interpret this as gravity. But actually it's just space-time. That's why I told you in the beginning that if I have two clocks ticking, two clocks living in different points of space, they will tick differently. But this is gravity, is not a consequence of gravity. This fact is exactly what we call gravity. So that's general relativity. And that's why we need curved space-times and we need all of these things, because I mean there is no other way. We know that when we are free falling we feel no gravity. We simply know this. And then no, I'm going to stop here because now we start describing mathematically all of these things. So this is the introduction that says that we are not doing differential geometry because I mean we don't like students. We want students to suffer. No, it's because there is no other way. That's the only way to do the thing, to describe gravity and to describe space-time. That are the same thing. So we need to change the things. One of the consequences is that a vector cannot be thought as being an arrow, because try to put an arrow between linking two points on the surface of a sphere. You cannot do this. But we can define vectors at every point of the sphere. And that's the way we do calculus there. That's the way we build reference frames, and that's what we will see tomorrow, how we do this in practice. So that's all for today, guys. Otherwise, it's too much. Unless you want to continue. But it's more than an hour. I can keep going, but I mean, we're going to have into mathematical details now. No, I think that's too much. It's too much. I mean, we keep. Oh, so that's the point is that at a certain point, people stop thinking about things and stop looking at them, paying attention, deep attention, because it's difficult. Well, we will return tomorrow. Yeah, it's a long break. It's a long break. But of course, I can discuss this with anyone that's interested. Just knock on my door. It's 102 at the second floor here. I'll be there all day long. So that's all. And of course, I'm fully open for questions.